All right, in Concept C, we're going to be looking at how to write formulas using various information. So we want to be able to apply the rules to assign oxidation numbers, and we also want to be able to write chemical formulas for both ionic and molecular compounds. So we're going to go over some different strategies on how to do that. All right, so some compounds are made up of ions, such as in ionic compounds, while others are made up of neutral atoms, such as in molecular compounds. Regardless of whether it's made up of ions or not, every atom, when we have a compound, has an apparent charge, and we call this apparent charge the oxidation number, which some of you guys have noticed already on the periodic table in your reference tables. This represents the charge of the atom if electrons were transferred completely. So we can use this information to predict the ratios when atoms form various compounds. So the periodic table only shows the most common oxidation states of all the elements. It doesn't include all of them. So sometimes you might find later in this unit that you get an oxidation number that isn't on the periodic table. That doesn't mean you're wrong, because these are only the most common types. You may come across ones that aren't listed. So rules for assigning oxidation numbers. An oxidation number of every atom in a free element or uncombined element is 0. So this includes any formula that only has one chemical symbol in it. So for our free elements, we would say that neon has an oxidation number of 0, Cl2 has an oxidation number of 0, a lead atom by itself has an oxidation number of 0, and N2 also has an oxidation number of 0. These are all examples of free elements, so they all have an oxidation number of 0. In a compound, the algebraic sum of the oxidation numbers must be 0 because compounds are neutral. So we're going to see that barium chloride is a +2 and each chloride ion is -1. Well, if I add up the sum, I have a +2 and then I have 2 -1s, which means then that 2 minus 1 gives me an algebraic sum of 0. Same thing here with sodium hydroxide. Na we're going to see is +1, oxygen is -2, hydrogen is +1, and I have one of each, so we're going to see +1, -2, +1. If I find the sum of that, I get 0. So these are all neutral compounds, and all of their oxidation numbers add up to 0. The oxidation number of a simple ion is simply its charge. So for an iron ion that has a charge of +3, that means its oxidation number is +3. This chloride ion has an oxidation number of -1 because it's going to equal the charge of the ion, and same thing for calcium here. It's going to have an oxidation number that's equal to the charge of the simple ion. In a polyatomic ion, which we mentioned before, the algebraic sum of the oxidation numbers must equal the charge of the ion. So instead of setting these equal to 0, I'm going to set them equal to -1. So I'm going to find that oxygen is -2, which means in this case that my nitrogen is going to be +5. And we'll talk about how to actually find that over the next couple of concepts. So if I look at this, I get a +5. I have 3 -2s, which means I have a total of -6. So I get my -1 charge. Same thing here. The sum of these elements have to be equal to -3 instead of 0. So I can find, in this case, phosphorus by using this idea that oxygen is a -2 and I have 4 of them. So it's -8, which means then that this phosphorus must be +5 because a +5 minus 8 does give me a -3. So I have equaled the charge here. Be very careful. You may want to think about this as putting this in parentheses, that this -3 applies to the entire PO4, okay, which is why we're setting it equal to PO4. This number up here does not go with the oxygen. It goes to the entire polyatomic ion. All right, group 1 metals are always going to be +1, and group 2 metals are always going to be +2. So when we're assigning oxidation numbers, Na is group 1, so I would assign that +1, and then Sr, which is a group 2 metal, is always going to be +2, which you can also find on your periodic table. Any fluorine that you see is always going to be -1, and the other halogens are also going to be -1 as long as they're the most electronegative element in a compound. So in this case, fluorine is going to be -1, and chlorine, it's written second, and if I check the electronegativity values, it is more electronegative than strontium, so I could also assign each chlorine a -1. All right, Hydrogen, most of the time, is going to have an oxidation number of +1. The exception is when it's bonded to a metal and it takes on an oxidation number of -1. So in this first example, chlorine is bonded to a nonmetal, so it's going to take on a +1 charge. Okay, here the hydrogen is bonded with a metal, so because of that, it's going to take on a -1 charge. Okay, most of the time we're dealing with it being bonded to other nonmetals. For the most part, it's going to be pretty rare when we come across a metal hydride compound. And then oxygen is usually almost all the time going to be -2. There are two small exceptions when it's bonded to a peroxide, such as H2O2. It has an oxidation number of -1. And then when oxygen is bonded to fluorine, because fluorine is so electronegative, it takes on a positive oxidation number. So in this case, we're going to see that oxygen, this is a normal situation, is going to have a charge of -2. This is one of the exceptions. It's bonded to a more electronegative element, fluorine, so it's actually then going to take on a +2 charge. All right, so let's actually apply these oxidation number rules. If an ionic compound, if that's what you have, and you've indicated that by finding a metal or finding a polyatomic ion in it, the positive ion, such as the metal, is always written first, and the negative ion, such as a nonmetal, is always written second. In a molecular compound, similar idea. The element with the positive oxidation number is always going to go first, and the element with the negative oxidation number is going to go second. And you're going to see that the element with the positive oxidation number is usually the one with the lower electronegativity, so it's more metallic-like than the one with the negative oxidation number. Once you determine the oxidation number of each element, we have to balance out the total charges. So all my positive ions' total charges have to equal all my negative ions' total charges. So we have to think about how many of each ion must we have in order to balance out the charges. Okay, they always have to add up to 0 as long as it's a neutral compound. All right, so we're going to do two examples here. Our first one, is chlorine and hydrogen. If you can get the slide back. Thinking about it. All right, so we know that hydrogen, when it's not bonded to a metal, is going to have a +1. I'm just going to write this here for the moment just so we can figure out with the order that we're going to write this. Chlorine is more electronegative than hydrogen, so it's going to take on a -1 charge. So hydrogen is going to be written first, chlorine is going to be written second. We said hydrogen was +1. The chlorine is -1. Because this is +1 and this is -1, I only need one of each, okay, to equal 0. So my formula is HCl. Sodium and oxygen. Sodium is a group 1 metal, so that's going to be +1. Oxygen, this is not one of the exceptions, so we know from our rules it's going to be -2. So I have NaO. Sodium, each is +1. Oxygen is -2. Keep in mind, when I put these numbers up here, it's applying to one atom of that element. Now, what I see here is that I have a +1 for each sodium and a -2 for an oxygen. In order for this to equal 0, okay, I'm going to need two +1 charges. So I'm going to put a subscript in after the Na. So right now I have two +1 charges, so I have a sum of +2. And then oxygen I only have one of, which is -2. +2 minus 2 gives me 0. So my official formula for this is Na2O. The main difference for handling compounds, and ternary compounds have 3 atoms, or 3 different types of elements, I should say. We always want to place the polyatomic ion in the parentheses. So when you see 3 or more different types of elements, look for that polyatomic ion using table E, and then place it in parentheses. Never change the formula of the polyatomic ion as it's shown on table E. You're just going to show how many are in a compound. So another teacher at Shen says if it's on table E, let it be. Don't mess with the numbers. So here we have zinc and phosphate. Okay, zinc, we have a Zn. Phosphate is PO4. Okay, zinc takes on a +2 charge, and then PO4 is going to have a -3 charge. Now this is where I want you to place this into parentheses, because I don't want to touch or mess with that 4. And then remember, I want this to add up to 0. So I can't just double one to equal the other. So I'm looking for a common factor here of 6. So I want this to add up to +6, and I want this to add up to -6. In order to do that, I need 3 zincs in order to get a +6. So each zinc is +2 times 3 is +6. And then each phosphate is -3. So to get to -6, I need 2. So negative 3 times 2 gives me negative 6. And then I equal 0. So that's my final formula, Zn3PO4 2. Here I have sodium and carbonate. Sodium is Na. Carbonate is CO3. Okay, carbonate's a polyatomic ion, so I'm going to place it in parentheses. Sodium is group 1, so we have +1. Carbonate is negative 2. And again, remember, I want this to equal 0. Okay, so I have a +1 and negative 2. So I could double how many sodiums I have to equal the negative 2 that one carbonate has. So I can place a 2 here as a subscript. +1 times 2 is going to give me a positive 2. I only have one carbonate atom, so that leaves me with negative 2, +2, -2 gives me 0. So my formula is Na2CO3. And you could rewrite that without the parentheses because we only have one of them, and that would be acceptable. Here we actually have two polyatomic ions. We have NH4, which has a +1 charge, and then sulfate, which is SO4, which has a negative 2. And remember, I want this to equal 0. So in this case, I need 2 of these +1 charges to equal the negative 2. So I'm going to put a 2 on the outside of the parentheses. So +2 or +1 times 2 gives me a positive 2. I have one SO4, which is negative 2, which equals 0. So my final formula here would be NH4, 2, and then SO4. I can then go ahead and drop the parentheses because I only have one of them. All right, so a shortcut for this is the crossover method. You're going to look up the oxidation numbers, and what's going to happen is that the oxidation number of the first element is going to be the subscript of the second, and the oxidation number of the second element is going to become the subscript of the first. The big point here that I always see the mistake of is that we cannot have negative subscripts, so you always are taking the absolute value of that oxidation number, and also making sure that any ionic compounds are reduced. So here we're going to deal with aluminum and oxygen. We're going to use the crossover method. So aluminum is +3, oxygen is -2. So what I'm going to do is I'm going to cross over my 2 to become the subscript for aluminum, and then my +3, taking the absolute value, I'm going to place as the subscript of the second. And what this does is +3 times 2 is +6, -2 times 3 is -6, which causes this method to automatically balance out my charges to equal 0. So my final formula here would be Al2O3. Here I have zinc and chlorine. Zn is +2. Chlorine is -1. Okay, I'm going to cross over my charges. So zinc would have a subscript of 1. Chlorine would have a coefficient of 2, meaning my final formula is ZnCl2. Hydrogen and oxygen. Hydrogen is +1. Oxygen is -2. And again, I'm just getting these rules from my list in the notes earlier for my rules for assigning oxidation numbers. I'm going to cross over my numbers, remember absolute value, so H2, moving the 2 across, O1, meaning my final formula is H2O. All right, so we are going to practice this a bunch tomorrow because this is definitely an important skill, and we'll work on both the shortcut as well as the understanding of calculating the algebraic sum.